Today we'll be talking about adding and subtracting numbers that are in scientific notation. First, let's look at the situation where the power of the 10 have very different exponents. This is 4.2 times 10 to the 6th and 3.1 times 10 to the 2nd. If we were to convert those into normal numbers, that's a 4, 2 with 5 zeros. We're talking 4,200,000, where this is a 3, 1 with 1 0. Now 310 may seem like a large number, but in comparison to over 4 million, it's relatively insignificant. When you're adding two things, the vastly different sizes, you pretty much just have the biggest number. For example, if I took the weight of an elephant and added the weight of a mouse, that's pretty much just going to be the weight of the elephant. The weight of the mouse is too small to be significant. In this case, 310, or 3.1 times 10 to the 2nd power, is too small to be significant. Let's see what happens if our exponents are the same. Now this is really nice. If you've been in my class, you've heard me discuss the apples to apples rule. The apples to apples rule applies to all addition, whether you're adding decimals, whole numbers, fractions, or things in scientific notation. And what it says is, if you are adding or subtracting numbers, they have to be the same kinds of things. This is why you need common denominators. This is why you line up the decimal. But a simple example is, if you have 3 bicycles plus 2 bicycles, that gives you 5 bicycles. But if you have 3 bicycles plus 2 race cars, those are not numbers that you can add together. Here I'm adding, and this 10 to the 5th, think of this as the kind of thing you have. I have 2.6, 10 to the 5th. Here I have 9.1, 10 to the 5th. Because they're the same thing, when I add them together, I am going to get something times 10 to the 5th. Now all I need to do is add these two numbers up. And I'll come over here, 2.6 and 9.1. Add those, and I get a 7 and 11. So I get 11.7 times 10 to the 5th. Now this is almost in scientific notation, but it's not quite, because 11.7 is larger than 10. I need to change that to 1.17 times. Now because I made this smaller, I must make this bigger. 10 to the 6th power. And that is my answer. 2.6 times 10 to the 5th plus 9.1 times 10 to the 5th becomes 1.17 times 10 to the 6th. Well, what happens if they are not the same thing? Well, if they aren't close, we already discussed that. If they are close, we'll do this. Now, they really need to be within 1. If they're within 1, that means one of them is about 10 times bigger than the other one. That's quite a big difference. If you have more than that, you're already around 100 times bigger. But here within 1 bigger, so now I can try to add these together. Now what I'm going to want to do is make it so both of these are either 10 to the 6th or 10 to the 5th. I find it easier if I take my smaller exponent and make it larger. So I need to change this 10 to the 5th power to a 10 to the 6th power. Now over here I made it larger. So to balance it out, I need to make this smaller. So 7.5 becomes 0.75. And this one stays the same. Now because these two things are both times 10 to the 6th, I can just add them together. 6.2 and 0.75. Add those. 5 plus 0 is 5. 2 plus 7 is 9. And I end up with 6.95 times 10 to the 6th power. Now I'm going to look at this and say, is this in correct scientific notation? It is, so I can leave it alone. Now, everything I taught you applies to subtraction as well as to addition. But let's just do an example problem of a subtraction. Here I have 4.9 times 10 to the 9th minus 4.1 times 10 to the 8th. I want to change this 10 to the 8th to be a 10 to the 9th. So that got bigger. If this one gets bigger, this one must get smaller. 0.41. This one just stayed the same. 4.9 times 10 to the 9th. 4.9 times 10 to the 9th minus 0.41 times 10 to the 9th. I can subtract these without any difficulty because they're both 10 to the 9th. My answer is going to be 10 to the 9th. Now come over here. 4.9 minus 0.41. Put a 0 there. Borrow from that. And I get a 9. And then I get a 4. And there, 4 minus 0 is 4. So I have 4.49 times 10 to the 9th. That is incorrect scientific notation, so I don't have to make any changes. That's my answer.